Okay, so this is the video about the molehill. This also includes like Avogadro's number, that's where this comes in. So the molehill itself is it's a visual tool, as you'll see below, that aids in converting between mass, moles, and particles / atoms, using the molar mass of an element or a compound, as well as like Avogadro's number. Wait, let me see here. Okay, so Avogadro's number is equal to 6.022 times 10 to the 23rd power. This can have more digits if you want it to, but I usually just stick with this. It's easy. But if you ever do need more digits for any reason, you can just look it up on the internet. The blessing and the curse of the internet, right? Okay, so the molehill. When we talk about moles, what are they? Moles, they're not the animal. They're not the skin issue. Moles are, essentially almost like a universal unit to kind of help tell you, how much of something there is, specifically when it comes to, elements, compounds, stuff like that. Things that are, very small, like atoms. And because of that, with moles being universal, you can convert the mass of an element to moles. You can convert the number of particles to moles, and you can do that interchangeably. So that helps you take the value. Like, say you have 30 moles of oxygen, but the formula you have wants mass. You might think, oh, I can't solve this. They didn't give me any information to solve this with. They did. All you have to do is convert the moles that they gave you to grams, and bam, now you have the mass that you need for that formula you're using. And vice versa for particles, atoms, and so that's really important. You'll find that this, it comes through with everything, which is why we're covering this topic, even though it's simple, easy. It's just because it's so integral. It goes into every problem that you do, at least the more complicated ones. If you don't know this stuff, it'll really hurt you in the future. Okay. Oh, and also, so moles I always forget it, but it's something like moles are equal to like a certain number of carbon, like on a lockdown facility. It's like, again, you can look it up. It's not important for the math, but it is interesting to know what a mole is, what tells you what it's equal to, so that's an interesting thing. It's weird thinking that there's a, lockdown, piece of, I don't know, fucking carbon somewhere that's like, we need to measure this and make sure it's correct, Anyway, I could also be totally wrong about that and getting things mixed up. Okay, so anyway, so what you'll see is when you're going to moles, you're dividing. When you go away from moles, you're multiplying. So when you take, just to remind you, or not remind you, but just let you know, the MW here on this side stands for the molar weight, or like the molar mass of an element. And so, this can get a little confusing, but not really. It's just like, as long as you know the basics, then you're fine. There are some elements that are diatomic molecules. Oxygen is a great example. Oxygen doesn't like being by itself. So in nature, it is typically found as O2, not O1. And so because of that, when, say, someone says you have, 16 grams of oxygen, the molar weight you're going to use for that, unless they specifically specify that it's O1, if they just say oxygen, it is going to be O2, because oxygen is just, at its natural state, is a diatomic molecule. And there are a few other elements like that too. So it's a good idea to keep track of that kind of stuff. In addition, when you have a compound, you have, fucking ammonia. I think that's NH4. I could also be totally wrong. When you have that, what you do to find the molar weight of that compound is you add up all the individual molar weights. So in the case of NH4, you have the N, nitrogen, So you take the molar mass of nitrogen, and then you have the H4. And you take the molar mass of hydrogen, and then you multiply that by 4 because you have 4 hydrogen atoms. And then you add that total molar weight of hydrogen with the molar weight of nitrogen. And then you get the molar weight of the compound as a whole. So the reason why I'm explaining that here is because I don't feel like that's a big enough concept to go over in a separate video. In addition, it's also it's pretty in there in my brain as being common logic. So not something I feel like is going to need reminders on, but just in case, there's this video. This video says it. Okay, so when you're going from mass to moles, you divide by the molar weight. When you go from moles to mass, you multiply by the molar weight. And then when you go from particles to atoms, it's not particles to atoms. When you go from particles / atoms to moles, it's dividing by Avogadro's number. And then vice versa, when you go from moles to particles, you multiply. So in a way you can think of it, I want to use a different color there. Don't want to mess up my whole system here, all my color coding and stuff. But I will do it in a different color to make it stick out a little bit. Because that was a connection that I made when I was drawing this out for this OneNote. So this is a new connection. So when you're going 2 moles, you divide. We're going away from moles, you multiply. And then when you have moles to atoms or vice versa, you're using Avogadro's. And then when you're going from mass to moles or vice versa, you use the molar weight or the molar mass, whichever one. Some people use molar weight, some people say molar mass, but mass and weight mean the same thing. But you'll see some people might do MM or MW, molar mass, molar weight, but they're the same thing. I don't know why there isn't people say it. I wish people would determine only say it this way. That would make things a lot easier. But they don't, at least not that I'm aware of. So, okay, so this is just a cute or a helpful little cheat sheet just for a quick glance. Because, one of the things that sucks about my memory is I for example, I will know all the conceptual stuff about the molehill, what it does, how to use it, but I won't remember the molehill itself. So when it comes to stuff like that, where you just can't memorize it, coming up with little things like this can help. And there's some things where you'll always need the visual for it, and that's okay. But you can always try to make it so it sticks in there without the visual. So always give that a shot. Even if it didn't work before, try again. You never know when it'll stick for good. Okay, so now that we've gone over, all this stuff, all the rules, now we can actually apply it. So I ended up compounding these problems. Instead of making multiple problems covering different things, these problems are kind of 2-step problems. And that just saves some writing space, but we'll be solving them kind of separately, and you'll see what I mean. So I've included the molar mass of these, which is carbon and lithium. Those are the elements that we use in these problems. And I chose those elements because they're not diatomic molecules, because, we can cover that in the diatomic molecule section. We don't need to cover that in the section that's specifically teaching us about converting moles, atoms, and mass. It doesn't make sense. It just adds an extra complication where it's not needed. So in this case, just pick some simple problems, made nice and easy. Okay, so now we're going to explore that. So we have convert 10 grams of carbon to moles. So we go back to Molehill. So we have grams, which is mass, and we want it to go to moles. So we're going from here, mass, to here. So we divide by the molar weight. And I'll show you something here, but okay, just remember we're dividing by the molar weight. So in this case, we have, and I'm also going to add, we're not going to pay attention to sig figs. 10 grams. And I have grams per mole. So remember here, we already said it's dividing, but just for example, we have grams over moles. That's what this is. This slash here means divide. And when you write it like this, it can be hard to translate that, to remember that. So when you write it out like this, it helps. What you realize is when you do this, what you'll end up is with grams squared and moles. That's what you'll end up with, and that's wrong. And so that just that logic piece of, that will help you remember, what you need to do. So, okay, so we have 12.01. Maybe we'll do sig figs. I don't know. I'll figure it out. So this is correct. So think about it. You now have grams over grams. It's just like, that. These cancel out. That's what you want, because, that the purpose of this is to convert to moles. So you want to get rid of the grams. So the grams here cancel out. So you have 10 divided by 12.01. Yeah, so we're going to round to sig figs because it's a crazy number. So, you can go back to a previous video if you want to renew this knowledge, but we're just going to assume that you know this knowledge. So the 10 here has no decimal, so only has one sig fig. This one down here, 1, 2, 3, 4, has 4 sig figs. Now, yeah, fuck it. We'll go with that. So that means, with division, that means we're going to use the 1 sig fig. So I'll write down the full number, or at least, yeah, we'll just write down the full number. So that's the full number. So I'll just round that to sig figs to make it easier to read. So that will be 0.8 moles. So also the interesting thing you want to keep in mind here with this, it's confusing sometimes, sometimes you have to think about it, but what you really have is you have grams over grams for moles. And so because of this, the mole is this thing right here, it's, under a division, the mole here is equal to just a regular mole. Because it's almost like the fact that it's on the bottom, but this is, if it was on the bottom, it would be, mole to negative, or, negative moles, whatever. But because you have it underneath, and then underneath it like cancels it out. So it makes it back into regular moles. It's strange. It's confusing, but it is what it is, man. It is what it is. Okay, so now we have moles. And we even rounded it to sig figs because, we're just that cool. But now we're going to convert carbon moles to number of atoms. So luckily, we've already found moles. But if you remember from, the sig fig lesson, when we solve problems, we don't want to, use the sig figs or, apply the sig figs before we solve. So we're going to write the full number that we got. Moles. Oh, and also keep in mind, if you don't write moles here on a lab report, they'll mark you down for that. You want to write it. I didn't include it here just for ease, of reading, but you do need to include that. It's important because it tells you what this number is. And sure, the next part here clarifies to you, if you didn't include the moles, it clarifies to you that it is moles. But it's just not very, like, quote unquote professional to do that, because who knows, maybe you have numbers that are very similar here. Maybe this is the arrow of another person's writing that could mean conversions, and so these could actually be different units, who knows. But so that's why it's important. Okay, anyway, go back to what we're doing. So we have moles of carbon here, and we will convert it to the mole number of atoms. So we'll go back to Molehill here. We're going from moles to atoms. Moles to atoms, you multiply by Avogadro's number. And we have that number right here. So what we get, we want to multiply by Avogadro's number, 6.022, which is Avogadro's number. And remember, this number doesn't count towards the sig figs at all, but this one does. We know it has one sig fig. Oh crap, that's like an OCD thing. I can't have different ones. It freaks me out. Okay, so now we do the multiplication. Oh, wait a second. I'm not sure if I included it. Let's make sure I included it. Yeah, I did. 10 to the 23rd. Okay, I was just making sure. I never do that. Well, that just, goes to remind you that you just gotta double check your work, man. Times 10 to the 23rd. That's Avogadro's number. We're gonna put that in parentheses, just for the sake of PEMDAS. So now we do the 0.83263946 almost did an 8. 7 moles times, and then parentheses, 6.022 times 10 to the power of 23. We get kind of a crazy number. It's in scientific notation because of our calculator, but we're just going to go with it. So this 1 sig fig, it's a crazy number, so just go with me. I'm not going to write it. 5 point. So you put the decimal there. I mean, it'll still be significant to 1 without the decimal, but the point of including the decimal here, even though it's 1 sig fig, is because it has all those decimals there. You just rounded it. And so this decimal serves to tell you that this 5 isn't just a whole 5. It has other stuff to it, but that stuff isn't significant, So that's why we include that decimal there anyway. And in this case, it's, 10 to 23rd. That's just because of, what my calculator did, because there's only a certain number of, numbers the calculator can actually show. So that's like how many atoms. So essentially what this is saying is that you have 10 grams of carbon that is equal to this many atoms, and if you multiply that number, you like a, crazy number, you get, if we even just put it in our calculator, 5 times 10 to the power of 23, this number is just gonna be like 0, 0, 0, 0, 0, because that 23 is moving that 0. And remember, because it's positive, that means it's going to be like, move to 23, so it's a fuck ton of atoms. Atoms are really tiny. It's a lot, because when you look at this number alone, you might, without considering the scientific notation, it might seem like there's only 5 atoms there, but it's much more than that. It's more like 5 million or something, and I don't feel like figuring out exactly what it is though, but yeah, so that also just tells you, like, you can convert by converting, because you don't even have to have this here. Say example, the problem said convert 10 grams of carbon to number of atoms, you could still solve that. You just convert to moles first and then use that to solve for atoms, so that's helpful. Next part. So we're going to take 5 moles of lithium to grams and solve for number of atoms. So this time, starting at the middle of the Molehill, rather than here, we converted from mass to moles and then use that mole number to convert to atoms, right? But this time, the numbers we're solving for, which is going to be moles to mass and then moles to particles, they're not going to go with each other. They're their own equations. So in this case, we have 5 moles of lithium. And so this is 1 sig fig, okay? Just putting that out there, because remember what we figured out. It's still significant without the decimal. This decimal here is needed because of uncertainty, and all the other decimals that are there, they exist. But here, no decimals exist. This is an exact number, okay? And then so we take the 5 moles and convert it to grams. So let's go back to where we were. Moles to grams, what do? We multiply by the molar weight. We can use the same thought process we went in over here, but that's there. So 5 moles times 6.941 grams per mole. So you have moles on top, moles on the bottom, they cancel out. And then an important thing to remember here is this molar mass is an exact number. Similar to like Avogadro's number, that doesn't factor into the sig figs. This number doesn't contribute either, because it's an exact number. Though I'm sure in some cases it does, but we're gonna treat it as an exact number right now. So in this case, we're only gonna pay attention to the 1 sig fig. By the way, the only reason why I say it's an exact number is because this number keeps going. You know, if you look it up, different websites will round it to a different number of decimals, but that number keeps going, you know, and most of them do. There are some of them that are exact. And so, you know, in that way, it's like, is it really an exact number? So I don't know. We'll go back to that. But as I'm going to reiterate, in this case, though, we're going to say it's an exact number. So when you multiply those together, you get 34.705. And we have the one. You know what? Fuck it. We used sig figs for the last one. We're just going to ignore it here. Just for, you know, why not? It just adds a whole other thing, because then we got to talk about scientific notation again. And I think this is enough. You know, the first one was enough. Okay. So we have this number, we get this number. That's grams. Remember, because this is the only one that wasn't affected in this grams. So that's how many grams is 5 moles of lithium. It's this many grams of lithium. Okay. Now we want to solve for the number of atoms. So remember, we go from grams to moles to, you know, atoms. Going from grams to atoms is not something that exists. So we don't want to use this number. We're already given moles, so this is much easier. You know, let's just go moles to atoms. And that's just like, you know, the logic behind it. So now we're going to go from moles to atoms. And remember, this is where Avogadro's number comes in. I think it's multiply, but you know, let's double check. Going from moles to atoms. Yep, it's multiply. We're going away from moles. This hasn't solidified yet, so I will do my best to start solidifying it. Okay, anyway, so you have 6.022 times 10 to the power 23. Put that in parentheses for PEMDAS, or else you'll do the 5 times 6, this number first, and then you do times 10 to the 23. No, you want this. This number is its own thing. Okay. So I go 5 times in parentheses 6.022 times 10 to the power 23. And you get 3.011 times 10 to the power 24 atoms. And that's how many atoms, or I'm actually going to show my answers. That's how many atoms can be found in 5 moles of lithium. You know, same thing. In 34.705 grams of lithium, you'll find this number of atoms. You know, they all go together. They're all the same thing. So yeah, I think that's it. Yeah. Okay, so to reiterate, you know, Molehill is you know, the name of that is for like a visual aid that we use to help remember how to convert between mass, moles, and, you know, number of atoms / particles. And then we use like Avogadro's number to do that, which has more digits, but this is just what I usually use. And we have, you know, all these simple rules over here, you know, simplified. And yeah, I think that's it for this one. Okay, so that's the Molehill.